So it is a delight for me to be here in the Institute, and it's even more honor for me to be here giving a talk in a conference in honor to Nicola Garofalo. So I met actually probably him last week, and I was thinking that maybe Nicola was the only, I have been thinking about that, I'm not so sure, but most probably he was the only mathematician that I have been following, reading papers since I was in Texas like 10 years ago, that I have never met personally. And I had the pleasure to meet him last week, and it's such a sweet person. We have been talking a lot, and so for me it's a great pleasure. It's actually an honor to be giving a talk in this conference in honor to you. And to prove that this is in fact an honor, so this is the picture in Fortaleza. This is my office in Fortaleza. When I was already here when we got this banner. Then I sent to a friend of mine back in Fortaleza, and please print it and put in my door, because I was so happy to be here. I'd like to show to my colleagues, show off a little bit. Okay, so happy birthday, congratulations to you, Nicola. Very nice. So what I'd like to talk to you today, it's a class of free boundary problems that they appear in random media, in discontinuous media, if you like. Maybe it's simpler to think about that. So let me use a little bit the talk of Aaron and make a picture of the two-phase problem, exactly the same two-phase problem that he just mentioned last talk. Let me change a little bit. So this is the way that I like to think about the two-phase problem. So you have a function u, which is it changes signs, and you prescribe a PDE in both sides, and also you prescribe a jumping condition along the free boundary. Okay, so that's the two-phase problem for me. Let me just mention some of the results Aaron just mentioned, some of the developments on the two-phase free boundary problems. Okay, so this is basically monotonicity formula. So as Aaron just mentioned, monotonicity formula is the key tool to study free boundary problems with two phases. So it all starts in this work of Altcaffarelli and Friedman in '84, where they, for the very first time, they introduced this monotonicity formula. And a few years later, Luis got the monotonicity formula for Hilbert continuous coefficients. So he allows divergence form equations with Hilbert continuous coefficients. So this theorem is the one that appeared in Aaron's talk. It took a while if you want to do the Laplacian with a bounded right hand side. So it took a while. This is a major gap from one to another. This was done by Luis, David Gerens, and Carlos Koenig, 2001. And but if you combine these two things, this can be done. We were interested in free boundary problems with in Riemannian manifolds. So this is one can find monotonicity formulas when the operator is like divergence form plus a bounded coefficient. And this Arshark and Matesvian got this in 2011. It's a companion work with myself and Lei Zhang. So this is basically more or less where monotonicity formula is known. But let me mention another problem which has to do with two different media. So so this is the kind of problem that I would like to think about now. You have an ice, and this ice is melting inside a different medium. Okay, so you have like your favorite juice, you have a scotch if you like, or some exterior fluid. Okay, So what happens is that when U is positive, when the temperature is positive, the temperature is ruled by a different operator. So let's say in this case it's A plus of U. And when you are within a negative temperature, you are inside the ice, so the operator, the temperature, is governed by a different medium, which is, let's say, A minus in this case. And as before, you also have this latent heat to melt the ice, which is given by this heat flux from one medium to another. Okay? So what happens in this problem is that even if, I mean, in this case, A plus and A minus, you can think about like bounded measurable elliptic operators. And, but even if they are different constant equations, okay, so take this is Laplacian and this is like 2xx plus 1/2 of uyy, you don't have monotonicity formula. So it's not that no one knows how to prove, it's that it's not true. But nonetheless, you can set up a variational approach to study this type of problems. And basically what you do is you minimize a functional where the A, you take into account U. Basically this A, I will put it here, A is A plus where U is positive and A minus when U is negative. You have the jump that you want, you prescribe your jump, and you can also put some forces, okay? So you choose your favorite F plus to put in the region where U is positive, and you take another function U minus and put in when U is less or equal than 0. So you can put like +1 and -1 depending on if you are taking out heat or including heat in each of the regions. Anyway, so let me mention that some warnings about this problem. So you can set up the variational setup is not much different from what you would do if you had like just the Laplacian, but some warnings need to be I need to mention. The first one is that it's not only that you don't have monotonicity formula for this kind of problems, is that even that functional that I described, if A minus and A plus, they are they are different, then the functional that you described is not convex. So even minimization, the existence of a minimizer is not, it doesn't follow from soft functional analysis. So this is, I already mentioned, if they are different constant matrices, you don't have monotonicity formula. And and there is here another threshold, is that even in simple equations, forget about free boundaries, even in simple equations like divergence of A of x d of u equals to 0 with A just continuous, without even jumps, but just continuous, then solutions to that equation with no free boundary fail to be Lipschitz. So these are three warnings to keep in mind to be able to know what you can say about such a general problem, such a general free boundary problem. So this is the first theorem that we were able to show, is that even though the functional is not convex, it always have a minimizer. You can always prove the existence of a minimizer. And here, I mean, F plus and F minus just needs to be in LQ for some Q greater than n over 2. It solves the expected Euler-Lagrange equation. So this Q is basically A plus in the region where U is positive, A minus where U is negative, is F plus when U is positive, is F minus when U is negative, and also take into account the flux balance that you are expecting through the free boundary. And moreover, we were able to get a de Giorgi type of theorem, okay, for these minimizers, is that they are universally Hilbert continuous. It doesn't matter much the Hilbert continuity here. The point is that they are uniformly continuous. So any minimizer any bounded minimizer automatically becomes continuous through the free interface. Okay? And this is universal in the sense that it depends only on the boundary, on the data of the problem. So like these norms, the norm of U, and the ellipticity constants of these matrices, and so on and so forth. Now, let me now make a stronger comment here. Is that in fact this problem, the way that I posted the problem, they are actually a evolutionary problem, and one should expect that. So you have your favorite drink, and you have ice, and the ice is melting inside this drink. So what happens is that when time passes by, the ice is melting and it's mixing with the exterior fluid. So at least near the free boundary where this change is happening, you should expect that the properties of the exterior medium becomes closer and closer to the pure water. So that's, you see, it's weaker Scotch. So what I'm saying is that it's reasonable to expect that when time passes by, these two limiting, I mean, if you are in a proper regime, these two norms are getting closer and closer in some sense, at least near of this phase transition. So this basically explains why it's important to look at problems with small jumps. Okay? So here's the theorem that we are able, by the way, this has been done with a PhD student in Fortaleza. He's now with Boyan Sirakov in PUC-Rio in a postdoc position. Is that is asymptotically Lipschitz, in the sense that, remember, that you can never reach Lipschitz even if you don't have free boundary. So this is the theorem, is that says that your equation is getting closer and closer to the graph of a Lipschitz function as the distance of the jump is getting smaller and smaller. Okay, so yeah, so basically this. So you give me any alpha less than 1, there exists a closeness borderline such that if the L2 norm of these two matrices near the free boundary, in the neighborhood of the free boundary, is close enough, then any minimizer of that function will be of class C0 alpha. So that's what I like to call C01 minus. So it's asymptotically Lipschitz continuous. And this actually, as a corollary, it gives you the following result, is that in continuous media, remember that in continuous media, even without free boundaries, solutions are not Lipschitz continuous. So if you have just one medium, which is continuous but not more than that, it's not Dini continuous, then minimizers are locally of class C01 minus. So it's asymptotically as Lipschitz as you want, never reach Lipschitz, but it gets closer and closer to Lipschitz. And this is in fact is a corollary to that theorem. I'm just
the result is independent of the free boundary.
Say again?
Your result is independent of the free boundary as a general.
Yes, you can. Yes. Okay. Yes, you see. Yeah, you can apply the result for something that doesn't have free boundary. Yes, perfect. So let me just say a word on the proof of these theorems. Is actually the way that we prove these theorems are on the reverse order. So let me just mention how we prove this theorem. First, we didn't prove like with small jumps and then get the corollary continuous. We did the other way around. We first take a continuous medium. You assume that you have a continuous medium. And what we do, we perform a geometric tangential analysis, more or less in the same spirit of the work of Luis on Schauder estimates for fully nonlinear equations back in '89. where you do like this sort of kind of what he likes to call Kors-Nirenberg type of estimate. So basically, if you have a continuous medium and A is close enough to the identity, which if it's continuous, I can always assume by doing a zoom in, then solutions are close to Lipschitz functions. Why is that? It's because basically what we are proving here is that in continuous medium, the Autka-Forelli-Friedman theory can be thought as the tangential free boundary for that problem. So I can get asymptotically. It's like a limiting argument, like argument for contradiction, that you make this go to 0, and at the end you have enough compactness because of the DiGiorgi type of estimate that we proved. You pass the limit, and you end up with a minimizer of the Autka-Forelli-Friedman. And therefore, you use the Lipschitz continuity available for that problem, and then you get the result backwards. And then we prove this theorem, which if you have two different media, it's C1 minus. How we prove that? It's the same geometric tangential analysis, but now you assume that A plus and A minus are separately continuous and with a small jump. So the tangential free boundary is going to be a one of this form. So for instance, if you are aiming C0 9.9, you use that the tangential free boundary has regularity C0 9.999, and then you use that, and it's slightly a little bit better than what you are aiming for. You have that, you have room, even though it's an asymptotic room, but you have room to make this improvement. So that's what I'd like to say about the proof. Sort of, yes. Okay, now let me mention about cavity problems in random medium, which I like to think about as the one-phase version of the previous problem. Okay. So there are tons of formulation. One of them, it's like the one that Aaron mentioned. It's like you assume that the temperature of the ice is always 0. You can think about a cavity problem, you can think about jet flows. There are several physical formulations of the same mathematical problem. The one that I like the most, which is related to my PhD thesis back in 2005 with Luis, is the following. I give you a heated body, D, and then one seeks for an insulation, omega, such that the heat flux is constant along omega. Okay? So this formulation actually is also related to Eugene's talk in this morning. So the picture is something like this. Okay, you have your domain D, which is heated. Let's say you have a temperature phi on D, and then you are seeking this domain omega, which is your unknown, such that the heat flux is 1 in a stationary situation. So this is basically what you are aiming to solve. So it's a Bernoulli type of problem. So if you put all this information in here in this box, what you see is the following. The function will be harmonic in omega minus D. It's identically 0, so the Laplacian is 0 outside D. And this is the information that you have. It's the u nu is equal to 1 along this free boundary. But I'd like to change that and say that using integration by parts. I would like to say that actually the Laplacian of u is, as a measure, charge 1 along the free boundary. Okay, so this is the same, it's just integration by parts. In the sense of measure, that's what you would like to say. So if you put all this information together, this is what you get, is that the Laplacian of u is equal to delta naught, so the Dirac mass at u. So it never charges when u is positive, never charges when the interior where u is 0, but through the phase transition, it jumps to 1. Okay? So you can ask yourself, how can you prove, so how can you develop an existence and regularity theory for this kind of equation? Okay, so you see I mean, it's okay when you're trying to solve Laplacian of u equals a measure. There is a lot of tools for that. But if you put the measure as as a potential, then it's not so obvious. But we can always interpret the delta naught as the derivative of the Heaviside function, right? So if you interpret the direct mass as the derivative of the Heaviside function, one is led to study this functional, which is what Luis did without in the beginning of the 80s. So that was what they studied. Now, one can actually study the non-variational cavity problem. So if you want to develop a non-variational theory for cavity problems, for instance, if you are willing to develop a parabolic version, which is actually physical relevant, you cannot use this minimization feature, right? But what you can do is that instead of looking at delta naught as the derivative of the Heaviside, you can see that as the limit of volume preserving L1 functions, like this. And you end up with the study of uniforming epsilon properties of this kind of equation. So delta beta sub epsilon is that approximation that I just mentioned. Okay? So what you do is that you try to get uniform estimates that are uniform in epsilon, and then you pass epsilon to 0, and then you hope for the best. Okay? And there are many works on this direction. Luis did work on this with Henry and Nirenberg, Claudia Lederman, Wolanski. They developed beautiful works on parabolic pre-boundary problems of this form. Arshart, Donatella, Enrique, many others. Aran also has work on Lipschitz estimates up to the boundary, and so I guess many people in this audience have worked on this kind of problems. So what would be a cavity problem in random medium? Okay, so I will take the randomness out of the table just to simplify things, and I will just look at equations in non-divergence form with bounded measurable coefficients. Okay, so this is the kind of equation. I would like to study uniform in epsilon properties of these solutions, viscosity solutions to that equation. Okay? Where Aij is just elliptic and just measurable. Okay? So if you want to study this kind of problem, actually, since your Aij is random in the sense that there is no continuity assumption on it, basically the only information you have is this. Okay? So it's like the Pucci of d square of u epsilon is bounded by this thing that is concentrating along the zero level sets of u sub epsilon, and the other operator. So it's equivalent. So if you want to study an equation and you do not want to commit yourself with any continuity assumption on the coefficients, this is basically what you are saying. Okay? So this is a thing that we have been doing with a PhD student in Fortaleza, another one. And this is the first result, okay? So if you give me a positive boundary data and fix an epsilon, there exists always a minimal solution. You can always solve this problem. Okay, this is the minor part. You can always solve this problem using Perron's type method. Fix an epsilon. And as much as we did the de Jord type of regularity for the two-phase, here we can do slightly simpler, a Krylov-Safonov kind of theorem for solutions of that problem. So in some sense, they are uniform in epsilon, C0 beta regular. Okay, so you can prove that there exists a modulus of continuity that does not degenerate as epsilon goes to 0. And let me just say that this is optimal. You cannot expect better regularity than that, just because you are with a bounded measurable coefficients. There are examples of subfunnel in R3. Solutions to a bounded measurable coefficients are just C0 alpha. You cannot improve that, okay? But you can ask yourself, what about the free boundary problem? Okay, so you take the limit. You have enough compactness because of this theorem. You can pass the limit. You can let epsilon goes to 0, and you are going to end up with a limiting equation, which is going to solve your equation in the positive set. Something is going to happen along the free boundary. And so this is basically what I was saying. It's, I mean, the solution is going to be just, when U is positive, solution is just C0 beta. There is no way to improve that, because you don't have any assumption on the continuity of the coefficients. But this is the result which comes in principle. I mean, if you have thought a little bit about this problem, it's not such a surprise, but at the beginning it sounds as a surprise, is that let U epsilon be the limiting solution. So you pass the limit, you get a solution, U is bigger or equal than 0, and take an interior free boundary point. Then at the free boundary, the solution is Lipschitz. So in fact, even though outside the free boundary, solutions are just C0 beta, at a free boundary point, you get Lipschitz continuity. So let me just mention a word on how these kind of things are proven. This is based on a new flatness improvement device, which reads like this. It's funny. So you give me any theta, you give me that. Okay, Nicola, which is the birthday boy, is going to give me the theta. And what I'm going to tell him is that with this theta, which is positive, I can find a delta that depends only on the ellipticity constants and theta, such that if you are now solving the equation with a delta multiplying the mass and the limiting function, let's say at 0 is 0, then at the ball of radius b1/2, this does not pass theta. Okay, so it's a sort of a flatness improvement device. It's not obvious when you write like this, because this delta does not depend on epsilon, cannot depend on epsilon. And if you write down this thing, you still have 1 over epsilon dividing here. So with delta fixed, this still blows up. But the intuition here is the following, is that if you have a solution, even if the Laplacian, even if the equation is the Laplacian, if you have a solution, a limiting solution, it may vanishes, be harmonic outside, but not be identically 0. Of course, these are the blow-up profiles. But if the free boundary, the limiting free boundary is 0, then the solution must be identically 0. So what I'm doing here is like as we did before, is like a geometric tangential analysis, having the equation which is 0 on the right-hand side, and the free boundary is identically 0 as the limiting equation. So these two information forces all solutions to be identically 0. And then I'm using this to prove that your function is flat enough. Okay? So that's, yes?
These U epsilon, are they the same you used to construct the limiting solution?
Yes, they are the same.
They satisfy then two equations at the same time? Because
which one?
The U epsilon.
No, yeah, very good point. It's this. We get this by a scaling argument. So you have you have your limiting solution. It's a good point. You have your limiting solution, and then you think at U of delta x. So this is gonna put and you look at U epsilon of delta x. This is gonna put a delta here, or square root of delta. Yeah.
This is just a technical.
Yes, that's the point. Yes, it's a technical, exactly. This is a technical step that puts everything together, and with this you can prove that, in fact, limiting solutions are Lipschitz at the free boundary. Okay. So Well, once you have done that, you can prove like non-degeneracy and Hausdorff estimates in the following sense. If you have now limiting configurations that come from minimal solutions, the ones that you build up from Perron's method. Recall that non-degeneracy in variational problems, they come from energy considerations. If you have a non-variational problem, you need to have a stable way of choosing solutions. It's not true in general, even for the Laplacian, that all solutions are non-degenerate. You have to be smart when you pick your solutions. But what I'm saying is that if your solution comes from Perron's method, then in fact, it's not only that it's Lipschitz, but actually there is a cone, it's non-degenerate cone, that forces you to enter inside of that cone at each point of the free boundary, which is basically this. So in addition, there is a delta, which has nothing to do with the delta from the lemma, such that the Hausdorff measure n minus delta is finite. Okay, so which I should say that I believe that. By the way, these are for random coefficients, so no regularity whatsoever. So I think that this should be optimal in this in such a generality, because I mean the free boundary should permeate. I mean there is no way to control where the free boundary will adjust itself, and it's probably gonna hit a lot of discontinuity of the medium. But you can ask yourself, in a slightly more organized media, can we get perimeter estimates, like the n-1 Hausdorff dimension of the free boundary? And you can ask, of course, I mean, if the Laplacian, this is well known, but you can ask what is the minimal organization you should ask so that you hope for a perimeter estimate. And this is what basically happens, is that if your Aij are in W1n, then indeed they are finite perimeter, and then you are in business. Okay, so if Aij is W1n, it's basically the minimal. I mean, I don't have a proof that if it's not W1n, then you don't have, but it's basically the minimal assumption so that you can do basically the analysis. Okay, I guess this is all I would like to talk about this cavity problem. Let me now mention about dead core problems. These dead core problems appeared in Catherine's talk yesterday. These are beautiful free boundary problems where basically the function vanishes in a plateau set without being identically zero. So the type of equation that I'd like to look at is like a general fully nonlinear elliptic equation with coefficients, and again, no restriction whatsoever on the continuity of the coefficients. In fact, we're thinking about random coefficients here. You could have like an omega random variable here. And it solves an equation like u to some mi, and mi is from between 0 and 1. So the case mi equals to 1, this is Catherine comment that yesterday. So just a simple application of a strong maximum principle, if a solution vanishes at one point, it becomes identically zero. Okay? You can always solve this problem. This problem, I mean, it is a free boundary problem, but it's a mild, there is a mild discontinuity per se. So existence follows by Perron's method is straight. And this is the key point. It's the same thing that I just mentioned about the cavity problem. Solutions are Hilbert continuous. That you get from Krylov-Safonov theory, because if U is bounded, U sub mi is bounded. So you have a fully nonlinear equation with bounded right-hand side. You don't care about whatever is there. It's just a like L infinite function. So it follows by Krylov-Safonov Harnack inequality that in fact solutions are Hilbert continuous. And again, you cannot hope for anything better than that, even if okay, I'll mention that in a second. Even if this is identically zero, solutions are just Hilbert continuous and no better than that. Well, if your operator is nicer, like the Laplacian, then solutions are C2 me. Basically because here you have a C0 me function, right? So they are C2 me everywhere. Then you can ask what happens along the free boundary. Can you say something more something more finer analysis along the free boundary? And indeed you can. This is improved regularity for dead core problems. This is the theorem. Take a non-negative viscosity solution to that equation with bounded measurable coefficients, fully nonlinear, and assume that Z is a point on the free boundary. So remember, everywhere else is just a Hilbert continuous function for some a beta that we don't know which one it is. Then at the free boundary, solutions are C2, 1 minus me. So you notice that me varies from 0 to 1. So this number is bigger than 2. So what says that solutions, even in bounded measurable coefficients, solutions hits the floor. Any solution hits the floor in a C2 fashion. So it vanishes in a smooth way, even though outside is just a C0 beta function. And also you remark that this is actually an improvement, at least along the free boundary, even if F is the Laplacian, where you can use Schauder estimates to say that solutions are C2 plus me, this number is always bigger than C2 plus me for any B positive. And you see that when me goes to 1, this goes to infinity, which would be saying that if you have a solution that with me equals to 1 that vanishes in a point, this would be an infinite order 0. Okay, so this is the picture. So where you as positive, you have like a C0 alpha roughness continuity, but if you do a zoom in, you will see a nice curve conducting the graph of U towards a smooth landing on the boundary, on the free boundary. Okay, so this is another theorem that we were able to show regarding these dead core problems. Is a Sharp-Bernstein theorem, which says the following: if you have like an entire solution to that problem with just bounded measurable coefficients, and let's say that U at 0 is equal to 0, then if U does not grow at least as 2 over 1 minus me at infinity, then U is identically 0. This is the Sharp-Bernstein theorem. And it's nice to see that when you prove this theorem, the fact that your regularity is you have a regularity. For instance, if you want to prove this for like analytical coefficients, when you write down the proof, you will need a regularity for bounded measurable coefficients, because you put this and you'd like to bring information from infinity to B1, you'll have to do a rescaling, and you will see that you lose any information if the coefficients, even if the coefficients are analytic, reanalytic. Okay, I don't want to say much about the proof of this theorem, and I would like to end my talk with just a set of results that we were able to show were basically in classical PDEs. So what happens is that in classical PDEs, you can try to import free boundary technologies and more importantly, free boundary insights to study them. So examples, for instance, there are these type of equations which are called MEMS type equations, where basically you have the Laplacian of U times f of U and f at 0 is 0. Okay, so this is roughly 1. So what happens is that when U vanishes, the diffusion of the operator vanishes. So everything collapses at those points, and I would like to understand what happens when U vanishes. So you can see this is a free boundary problem just by saying that the free boundary is going to be the set where u is 0. Even more classical type of equations like the Laplacian. So this is a nice operator outside the critical points where the gradient vanishes. So you can try to see this is a free boundary problem where the free boundary is the critical points. And there are many other examples, the generate elliptic operators, and even very simple equations of this type of form, the borderline sources, L of u equals g of x. So, and you have like borderline integrability condition of g of x, and would like to understand what is the best regularity you can hope for u. So you'll see that like as a free boundary, non-physical free boundary, where the free boundary is going to be the points where g behaves like a negative power of absolute value of x. Okay, so we do have results in all of these type of situation, but I'd like to get the most classical one to bring it to today. So let's revisit Schauder's a priori estimate. So this goes back to the 30s, where Schauder proved that if you have a elliptic equation with C0 gamma coefficients, gamma from 0 to 1, then solutions are C2 gamma, and this is optimal. There is no way to improve that. Okay, this is well known that this gamma is the best one. If gamma is equal to 0, solutions are not C2. If gamma is equal to 1, solutions are not C2-1. In divergence form, solutions are C1 gamma. So there is a lack of one derivative from one theory to another, and this is well known. Oops.
Let's see. Are you sure?
Yes.
You don't get C1 beta for beta less than gamma?
No, I think you got precisely the same one. It's C2 gamma, you get
For divergence.
the divergence. No, I think it's the same, isn't it? Is that the same? You got the same, right?
With Schauder type estimate.
Schauder type estimate. Good.
You construct you don't construct the solution variation, or you construct it using like a Schauder method.
Okay. Good, thank you.
No,
That was
it's C1. Yeah.
C1 gamma. And just before I show the result that I'd like to finish my talk with, let me just mention that we use that all day. Okay, Schauder estimates, we use this at least twice a day. When you go to the school, you are using Schauder estimate. You go there, get your office, you use Schauder estimate. We use that all. I mean, it's a day life thing, and sometimes we don't stop to think that this is in fact a sharp and non-trivial result in the following sense. Let's look at Poisson equations. So it's the simplest form possible of Schauder estimates. Laplacian of u equals f of x. And so Schauder estimate says that if the Laplacian of u is C0 gamma, then u is C2 gamma. Let's see this in the Haitian thing. So what Schauder is saying is that if I add the diagonal of this matrix, and if this gives me a C0 gamma function, I'm not even asking each one of them to be separately a C0 gamma function. It could be the case that there would some cancellations, but I'm not even asking that. If the sum is C0 gamma, then in an interior ball, all entries, even the ones that don't appear in the equation, are C0 gamma. Okay? So we don't stop to think about that. We use and think it's, well, this is okay. But in fact, it's a rather non-trivial result from this perspective. So Schauder estimates do carry a free boundary. So this comes as a surprising, because, I mean, if you think about it, there is no free boundary, there is no phase transition, nothing. But it does carry a non-physical free boundary in the sense that I would like to explain now. So the variational theory, it has a non-physical free boundary, as I was explaining, where the points are the set of critical points. So the points where the gradient vanishes. So the points where the gradient vanishes, for solutions to this variational divergence form equations, it behaves like a free boundary. And in the non-variational theory, you do have a non-physical free boundary, which is the point where the Hessian degenerates. So here's the ultimate result you can show is that if you have Aij just elliptic and Dini continuous, so in this case, this is the lowest case one where you can get like C1 and C2, at least the one that we know. Then if you have an equation, if you have a solution to this equation, and Z is a critical point, so in the way that I'm saying it's a free boundary point, then you jump from C1 to C1 1 minus. Solutions are C1 1 minus regular at a critical point. And in the non-variational theory, solutions where the Hessian vanishes are C2 1 minus at those points. So you jump from C1 to C1 1, asymptotically C1 1, and you jump from C2 to asymptotically C2. Okay, so just to explain this graphically, so this is the gradient or Hessian continuity from the classical theory in all those points, and which by the way are these are optimal results. But if your point happens to be a gradient or Hessian degenerate point, then you open this as asymptotically as a cone. Okay, and with that I will stop. Okay, thank you. Congratulations.
Any questions?
So I must apologize. I was thinking of Lipschitz continuum. You don't get.
Oh yeah, then you don't get Lipschitz.
C1 1.
I know this because I was thinking like you not long ago.
I'm sure you know.
You went and you build a solution, like you do freeze the coefficients and do a
I mean, the result doesn't carry all the way to Lipschitz.
Yes, it doesn't. Yes, you're right.
C alpha, C1 alpha, but Lipschitz does not imply C1 1.
Yeah.
Okay. All right. Sorry.
I was wondering about this a few slides back, about this little o at infinity, the solution.
Oh,
The
the dead core problem.
Leo ville
Bernstein.
Bernstein, right?
Yeah, something on little o.
Yeah. This is the one. Yes.
Yes. Don't you think that you can actually sharpen this by, because you can actually compute, this is the non-negative solution, yeah, then you can basically compute the global solutions in a linear case.
In the linear case, yes, you can hope to get global profiles.
So somehow it suggests that there is a constant, basically, which is the optimal C1 or whatever you have,
Yeah, this-
C2, yeah. So that's the optimal regularity, no conversion.
Mm-hmm.
And if you have something else that happens at infinity, which is slower than this rate, then you can sort of bring it down and get a contradiction.
Yes, this is more or less how the proofs go. But the nice part is that first of all you need to have this global regularity along the free boundary, and second and more important is that if you want to carry this proof and you have like analytic coefficients, then in fact you need a sharp regularity theory for bounded measurable coefficients. It doesn't help if your coefficients are reanalytic, because when you scale it back, you're putting a L sub x in front of the. So this is what was like.
What I meant is basically your local regularity.
Yes.
Uniform local regularity, which I believe wouldn't depend on the boundary data.
Yes, it doesn't. Yes.
And that means basically that there is a constant independent of boundary data. And that constant could be sort of replaced in here.
To say it's big O of less than this.
And I think this is the,
Yeah, I haven't thought about that. That might.
because this
Thank
is
you.
things that happen in obstacle problem.
Mm-hmm.
Fixed constant, which.
Yeah, that's. Thank you.
Okay, so we have the next talk starts at 4 o'clock. Yeah, thank you.